Hello, everyone. My name is Polong Lin. I'm a developer advocate. My focus is on data science and machine learning on Google Cloud. Today's topic is humans versus AutoML. It's going to be around how to improve your models with BigQuery ML. So let's get started. And now, the focus of this talk is how to build and train and deploy models with BigQuery ML. But the main bulk of it is actually going to be about how do you actually go ahead and improve your model once you've made your first one. And we'll go through a couple of different kinds of approaches on how you can improve the performance of your model, for example, with model selection, feature selection, and feature engineering. And then finally, I'll reveal some results around AutoML and how I compare against AutoML and how other humans have compared against AutoML, so you can get a kind of a sense of the potential power of AutoML. The assumptions that I'm kind of making when I'm making this presentation here is that you're already quite familiar with BigQuery. You could be doing some data analysis, or you could be processing your data in BigQuery already, or you could simply have some data stored on BigQuery, but you haven't really done a whole lot of things with it. My focus here is to help you understand what you could potentially do with BigQuery and BigQuery ML in particular, and how you can build these models and hopefully address some of your business use cases with machine learning. Okay, so that being said, hopefully this slide I won't have to cover too much, but essentially Google BigQuery is the data warehousing solution on Google Cloud. It's fully managed and serverless and fully scalable. So lots of bullet points here. You can go through this. I won't go through this here in detail. And critically, BigQuery is kind of the center and the heart of a lot of what we call the smart analytics solution within Google Cloud. And so what that means is whether you're bringing in data, whether it's batched or streaming, a lot of that kind of flows naturally to BigQuery due to lots of different integrations. And as you do processing or analysis in BigQuery, you can also create dashboards through Looker or other partner BI tools. And so essentially, BigQuery is quite a big piece of the data story. So when it comes to trying to create machine learning models using data that's stored on BigQuery, what could you do? So previously, you would have had to potentially export some of that data outside of BigQuery and then run your models and figure out how do you build your infrastructure and data pipeline. But now with BigQuery ML, you can do everything. You can build your models, deploy your models, all within BigQuery using SQL, and this allows you to speed up your development of machine learning models at scale and also in production as well. And it comes with all that kind of infrastructure, security, and compliance that you would already enjoy with BigQuery. So that's a big plus. So the focus of this particular presentation is around an e-commerce sort of setting. So if you imagine yourself going on an online store and you're interested in a particular product, you might add that to a shopping cart. But what about all the behaviors that might kind of lead up to adding something to a shopping cart? Because as soon as you add something to the cart, you kind of express this kind of signal, this very strong signal that you're rather interested in purchasing or potentially purchasing a particular product. So all the signal that's coming beforehand, so for example, the total number of times that you may have been clicking on items or products on a particular website, the amount of time you spent on it versus clicks, whether or not you've used a mobile phone versus a desktop computer to be able to visit the website. So there's a lot of different kinds of demographic and behavioral data that could be used with machine learning to analyze and to predict potentially whether or not someone's going to add an item or items to a shopping cart on an online store. And what better way than to try to analyze some of that using some public data that's actually from a real online store. So this is Google Analytics data that's coming from a real store. This is the Google Merchandise Store. And the Google Analytics data that's coming from this online store has been fully anonymized, and it's actually freely and publicly available. You may be familiar with it if you use BigQuery public data sets. It's one of those public data sets, but you can actually explore this data set. And so I've kind of shaped this in a way that it kind of lends itself well for machine learning by trying to predict whether or not for each of these visitors and their sessions, whether or not they're going to add something to the shopping cart. So essentially what that means is if someone behaves in a certain way and I build this machine learning model, I can pick that up, that I should be able to predict whether or not someone's going to add something to the cart. and at the end of the day, they actually didn't add anything to the cart, that's going to maybe raise a flag. And maybe I could go in as a business owner and say, it looks like you were interested or whatnot, and maybe provide some sort of incentive like a coupon to kind of encourage their business on the e-commerce site. So that's kind of the business premise. And so let's go ahead and try to build the model and kind of explore this. So in BigQuery ML, it's just four very, very simple steps. Even before BigQuery ML, you might imagine you could be doing a select statement. So here I'm selecting the full visitor ID, the country of the visit or the visitor, the total number of page views that the visitor has made during that particular session, and whether or not they added something to the cart. So this is a simple select statement, and then from my project.dataset.train. So just by adding a couple more lines of code in SQL, I can essentially create a machine learning model. So you'll see here in blue, create or replace model, and then my dataset.logReg. So in this case, I'm creating a logistic regression model, so I'm calling it logReg. And under options, I specify model type is equal to logistic regression or some other model that's supported. And then of course, you want to input what variable you're trying to predict. So in this case, this is added to cart. And then you select the training data that you want the machine learning model to train upon. Of course, in this case, full visitor ID is not going to be particularly relevant. So we're commenting that particular row out, that particular feature out. But everything there, it can run. And essentially, as I run this statement, logReg becomes an object within my data set. So essentially, if you have views, if you have tables in BigQuery Ready, logReg becomes kind of its own object under your data set. And essentially, that is ready to use. So what can you do with it? Well, the first thing you might think of, well, how did the model perform? So you can run select star from ml.evaluate, followed by model, and then the name of your model. Now what's happening is, in the previous step of create or replace model, it's actually splitting your data into a training and a validation data set. So when you run ml.evaluate directly, it's actually trying to evaluate it based off of the validation data set that it's done behind the scenes for you. So you don't have to worry about splitting your data beforehand. Now, alternatively, you could use your own data. So let's say you have your own test data. You could do that instead, and also get the evaluation metrics directly from there. So the evaluation metrics could depend on the type of model that you're using. It could be RMSE, it could be ROC-AUC, F1 score, accuracy, precision recall. So lots of different kinds of evaluation metrics are available with ml.evaluate. And then let's say your model is good or good enough. Then you may want to actually do the predictions. Because the model is in your data set, it's ready to be used for predictions. And all you need to do is ml.predict, and then followed by the model and the data that you want to predict over. And essentially, it'll create a new column, predicted underscore, followed by the variable that you're trying to predict, as well as some other confidence intervals and so on, depending on your model. So that is ml.predict, and that is essentially these 3 or 4 steps that make up a BigQuery ML model, making it super, super easy to be able to create your models on data on BigQuery. Now, here's some of the supported BigQuery ML models today. So some of these are in beta, so it's worthwhile to check which ones are GA and which ones are in beta. For classification, you have logistic regression, XGBoost, deep neural networks, and AutoML Tables. Regression, you have linear regression, XGBoost, DNN, and then AutoML Tables as well. For other models, there's clustering, time series forecasting, or ARIMA, which is used for sometimes for demand forecasting. You can also build recommendation systems or recommendation engines using matrix factorization. And then finally, if you have your models kind of stored outside of BigQuery, let's say you have a data science team that's working on TensorFlow models, you can actually import those TensorFlow models directly into BigQuery and then run those models on your data on BigQuery using those models that you had created elsewhere. And on the flip side, you can also export some of your models from BigQuery ML outside of BigQuery ML, so you can run it online as well. So lots of different ways in which you could use BigQuery ML. Now, I've mentioned AutoML Tables. So for those of you who don't know, AutoML Tables is essentially using the state-of-the-art kind of research that's been done at Google to be able to create the best possible model that it can strive for by looking through various types of machine learning models, here's just this list of models, and also different ways in which it's essentially engineering different features, imputing missing values or dealing with outliers. It's doing a whole lot of things behind the scenes. So essentially, AutoML is almost like this machine learning API. You send your data, and then it can give you a model back that has really, really high performance. So we're going to go through the process of improving or creating a model, trying to improve it manually by myself, right? And then finally comparing how that kind of compares against AutoML Tables. So we're going to try to beat AutoML Tables today. Okay, so again, this is the same use case, same data set. So my approach for modeling for this particular task, because it's a classification task, we're going to be doing all the kind of the classification models. We're also going to be doing feature selection, feature extraction, feature engineering. So each of these are slightly different. They're all kind of under this domain of feature pre-processing. Feature selection is choosing what features you want to use to build your model. Feature extraction is extracting kind of bits and elements of data that already exists in some of your features. Feature engineering is also kind of similar, essentially creating new features, typically based off of the features that exist already. So I'll go through some of these techniques that you can use to be able to augment your data and to improve your model. So at this point, I'm just going to quickly switch over to my BigQuery tab, so you kind of get a deeper sense of the data itself. So that's really important. So let's really kind of dive into the data set here. So this is my table on BigQuery. I've kind of zoomed in, so it might look a little bit strange. I kind of zoomed in so you can kind of see the column names, the schema, and also the preview as well here. Essentially, we have the full visitor ID, we have the date, device, and so on. Actually, it might be easier if you see it via the preview. So we have the full visitor ID here. The visit start time, this is in epoch time as an integer. We have the date here as well, but you can see there's some issues with it. It's not really showing the actual time, which is actually under visit start time. And then we have some categorical variables or text-based variables. So we have device category, tablet, mobile, desktop. Is mobile, whether or not the visitor visited using their mobile phone or something else. The operating system of that particular device, the browser, country, city, the traffic source as well, the traffic medium and traffic campaign that kind of tie into whether or not the visitor came in through a particular campaign via some sort of ad campaign. And then we have a lot of numeric kind of features as well. So whether or not the visitor came in as a very first time, was it their first visit to the Google Merchandise Store? Whether they bounced directly, that means they went to the site and then immediately left. The total number of visits, total number of hits, that's the number of interactions on the site, total page views, total time on site in seconds, total transactions, product pages viewed, and then finally, the label that we're trying to build a model around, which is added to cart, 0 or 1. Okay, so let's switch back to the slides here so we can go through some of the basic models that we could try to work with and then try to improve it from there. Okay, so the first thing that we can try to do is create a logistic regression model. And let's just select a few features that maybe off the bat we think might help. So you should at this point be fairly familiar with the query statement so far. You're creating or replacing the model, log reg. Input is logistic regression. We're predicting on added to cart. And the features that we're trying to use are country and total page views. Okay, so based off of this model, now I'm going to show you the results that I get. So I'm essentially saving some time for you by just simply showing the results. So you don't have to wait for these models to finish running. So in this particular case, the log loss is 0.12 and the ROC-AUC is 0.95. Now, a bit of a note on these two particular evaluation metrics. So sometimes people use log loss, sometimes people use ROC-AUC. And so for that reason, I'm kind of listing both of them. And it helps us compare between the models as we try to improve by adding more features and so on. Log loss, you want to decrease that as much as you can towards 0. And then ROC-AUC, you want to try to increase that as much as you can towards 1. So that's kind of the goal: decrease log loss, increase ROC-AUC. Okay, and so as a log loss decreases and as ROC-AUC increases, then our model performance is hopefully going to be better and better. Okay, so the first thing that we need to go through, we've talked about manual selection of some features. Now let's try to add some features corresponding to the dates. Actually, before that, I've forgotten. Let's try using all the features first and see what happens. So let's go ahead and just run logistic regression on everything except full visitor ID, and let's just see what happens from there. So if I run this particular model on all the features, you can see the log loss has increased a little bit, which is not good, and the ROC AUC has increased, which is good. So it's a bit of a mixed signal here, but overall it could help. Since we only use country and another feature in order to build log reg, the very first model, having at least some extra features should actually help. So it could be a little bit confused. Maybe some features are not really super relevant. So we'll kind of see from there. One thing that we noticed before was based off the data is that for date, the hour, minutes, and seconds were not actually there. And also the visit start time, there's some issues with that. So one thing that we can do is extract those features directly from those columns. So in this case, we can say, select and then do some extract statements. So extract the month, extract the day of week, extract the day, extract the hour from the visit start time by first converting it to a timestamp. And then let's try to run the model. But before we do that, I want to specify something that's actually really, really important here, because this could potentially create a big problem if you run your models like this. If you do select and then extract and then everything else from your data set. And the reason why this is going to be a problem is because when you run ml.predict, essentially you have to remember every single variable that you create. So you now have to run select, extract, extract, extract in the same way that you did when you built the model. And that's going to be a little bit difficult to maintain because you have to keep remembering, all these variables that you created from before when you built the model. So there's actually a solution to this, and the solution is to use what's called transform. And transform essentially is going to memorize, it's going to remember all these different ways in which you've processed the features, store that as part of the model. So when you run ml.predict, you don't have to run extract, extract, extract all over again, because it's going to remember all these transformations that you do on these features. So the model will remember your transformations when doing your predictions. So when you run ml.predict, you can just simply run ml.predict with select star. You don't have to do all those extract statements anymore, because transform has been included as part of your model, and so you don't have to use that anymore in ml.predict. So really, really important feature that I think everyone should do when you're trying to pre-process features. Now, the next thing is, of course, understanding how well our model performed, right? So we've now extracted the dates and the time just to understand whether or not this could improve our model. And what we see here is we've now been able to decrease our log loss, and we've now boosted our ROC AUC. So ROC AUC increased, which is a good thing, and log loss has decreased from the second model, so from 0.124 to 0.122, but it's still not that low. So there's still room to improve. But at least ROC AUC has increased. So we seem to be going in a positive direction. Now, something else that we could do is we noticed that there's this column called traffic campaign, and there's lots of words in this particular column. So how do we extract some more insight out of this? And as we do a select distinct from traffic campaign, we'll see that there's 8 different kinds of campaigns. We have accessories, all products, apparels, electronics. So there's different campaigns for different kinds of categories of products. Can we somehow find some more insight from this? Now, in your particular use cases for business, you could have keywords, you could have descriptions for products and so on, which I didn't include here. But in those cases, you would have the same problem. How do you extract more information from text-based columns? So one thing that you could do is super easy. It's called Regex Extract All. And what you can do is you can specify the regular expression to extract all the words from your features that contain text. So in this case, I'm using Regex, it's kind of hard to pronounce really, regular expression, extract all, on traffic campaign. And then you can see the extracted words are shown on the right-hand side in the second column. So we have not set, all products, AW, and then apparel AW, and then all the individual words, which is great. So this extracts out all the keywords, and I can run this and kind of feed that directly into the machine learning model. But before I do that, sometimes you may find that the the word ordering sometimes could really matter a lot when it comes to your text-based features. So for example, and this is a very common example, I live in San Francisco. Now, if you were to take the individual words out of the sentence, you get I live, well, if it's alphabetically sorted, it'd be I, in, live, Francisco, San. But if you were to take every two words that were kind of next to each other, so these are called bigrams, then it'd be I live in San, live in San Francisco. And the key thing here is that if you have other sentences that say, San Jose, trying to think of the other, San Jose, San Francisco, San Diego, right? The ordering of the words would actually matter quite a bit. And so in these sorts of cases, you may want to consider using unigrams, not just unigrams, but bigrams, or even trigrams, or I don't know the word for, I guess, quadrigrams or something like that, I guess. But you could do all sorts of these things by using ml.ngrams within BigQuery ML. So on top of the words that you've extracted, you can then run ml.ngrams, and it'll take all the combinations of the words in the right order. So in this case, I'm choosing 1 and 2. So I'm choosing for unigrams as well as bigrams. So you can see here we have not set, and set when it comes to the first row, and then for the second one, it's it splits based off of the hyphen because that's not a word. AW accessories, and then it accessories itself. So I've extracted the unigrams and the bigrams from the data set and created a new feature from that. So based off of this, how does our model perform once I've run ngrams on that particular feature? Well, we can see here our log loss has actually decreased. Great. And our ROC AUC is, it's decreased a little bit, not so good, but it's still, we could be going the right direction here. We're still trying to create more features, and we can see how our models continue to perform. Now, another thing that we can do is, we have a lot of numeric columns, as you saw from the table. And one thing that we can do is we can try to bucketize them or bin them. Essentially, what that means is if you have, time on site, let's say someone spends 0 seconds on the website, and someone else spends 1 second on the website, and someone else spends 2 seconds on the website. Well, it could be that they're not really looking at the website at all, even if it's 1 or 2 seconds. So maybe we should bucket those behaviors together into the same kind of behavior. And then maybe for those who are, between 10 seconds and 15 seconds could be another bucket. And then maybe 100 seconds plus could be another bucket. So what you can do is, again, based off of the quantile, you could bucketize all those numeric values within a numeric column and bucket them automatically using this feature called ml.quantile bucketize. So here, the only thing you need to specify is the number of buckets you actually want. So in this case, I'm specifying 100, kind of arbitrarily, just kind of thinking maybe 100 might help. It could be 10, it could be less, it could be more. But in this case, I just chose 100 just to see how it would work. So choosing 100, you can see here, I did a group by and count to see how many of the actual values would fall under bin 1, how many values would actually fall under bin 2 and 3 and 4 and so on. So you can see there's actually a huge amount of numeric values that fall within bin 1. I didn't check the value of this, but I assume a lot of that is zeros or 1 second spent on the site, or maybe 2 seconds spent on the website overall. And so that's really kind of bucketing all that behavior into a single label there. So quantile bucketize. So how does this perform? Now let's see. So by using bucketize, you can see there's a huge difference in log loss now. Huge, relatively speaking. It's now dropped to 0.092, and the ROC AUC has actually increased quite a bit to 0.97. So this is fantastic news when it comes to building the model. We've simply added buckets to all of the numeric columns, and now we've improved not only our log loss, but also improved our ROC AUC, which is great. So far, we've only been using logistic regression models, but what about some of the models that I mentioned earlier? So here are some of the models. So in addition to logistic regression, there's also XGBoost, deep neural networks, and of course, AutoML. But what are some of the differences between each of them? So in terms of the training speed, so logistic regression tends to be the simplest, but the fastest to train. XGBoost tends to be a little bit slower than logistic regression, but tends to perform overall better than logistic regression. And then DNN can sometimes be better than XGBoost, but typically takes a little bit longer, even longer than XGBoost to be able to train. So there's a bit of a trade-off between each of these different kinds of models. But between XGBoost and DNN, sometimes it can be a hit or miss as to which one is better. So I would recommend kind of playing around with both of them. But and sometimes even logistic regression could be better. But in terms of this particular use case, well, I guess I'm kind of spoiling it. We'll see. All right, so let's try XGBoost. So the key thing here, so everything on the right-hand side is everything you're familiar with already. The only thing I've changed is changed from logistic_reg to boosted tree classifier. And by changing it to boosted tree classifier, we're now running XGBoost. And what I like to do as well is in the naming of my models, I like to kind of prefix it with the model type. So here I'm using XGBoost, so I like to kind of add in XGB_ for all of my XGBoost models. That helps me remember exactly, oh yeah, in this model I use XGBoost, or in this model I used LogReg, or in this model I use DNN. So helping to kind of maintain my models based off of the name is one kind of little trick that I advise. So using XGBoost, how does it actually perform in practice? So using the very best logistic regression model from before was this very first row. So we had 0.09 in terms of log loss, and then 0.97 in terms of ROC AUC. And you can see there's almost a dramatic improvement by switching over to XGBoost. So in row 6, I've used XGBoost by just simply extracting the date and using all the other features to train the model. And here I've improved my log loss as well as my ROC AUC. And then the other thing I did was I also bucketized all of my numeric features as well and tried to rerun it. And you can see here again, log loss has improved 0.072, now a slight improvement. And also ROC AUC has improved slightly as well. Now I ran this without, these are scores without using the n-grams. It turns out by including the n-grams, so these are all the words from the text field for traffic campaign, it actually made the performance quite a bit worse. So it could be that the text in that traffic campaign simply was not highly available. There could only be maybe a few rows here and there that had the campaigns or whatnot. That would be worthwhile for me to investigate, but it just turns out that using n-grams did not improve my model, so I've simply kind of dropped it from at least from this table here, so it helps you understand how these models improve. Okay, so I'd like to introduce this other way of creating more features. We've covered quantile bucketize, we've covered n-grams, we've covered regex extract all, we've covered extracting dates and time from timestamps. So feature engineering is kind of similar. It's the idea of creating new features based off of typically other features that exist already. So there's two that I really want to highlight here. One is ml.polynomial expand, and the other one is ml.feature cross. So let's go through each of them one at a time and see how our models improve or not improve as a result. So the first one is polynomial expand. So if you just look at this table, focus on this table first, we'll see that we originally had this total hits column, and here we also had the total page views column as well. So what polynomial expand does is it combines every possible combination of these two variables and combines them by multiplying them together. So in the first column, we have total hits. That's the original data, original feature. Total hits underscore total hits is itself multiplied by itself. Okay, so total hits multiplied by total hits. And then we have total hits multiplied by total page views. And then we have the other column, total page views, which is the original column. And then we have total page views multiplied by total page views itself. So it's squared. So it's 22 squared is 484 here. So first of all, you might be thinking, wait, hold on. Why are we doing this? Why are we multiplying features together? Well, it could be that for some reason, these features are really important. And not only that, by taking the combination of these two features, you're actually magnifying the signal from these two features by either squaring it itself, by taking the interaction essentially between these two features, or by squaring, the second one. I've kind of repeated myself, but essentially you're kind of augmenting your data. You're creating new features based off of your existing features and adding things to potentially, and this is key, it's to potentially add more signal based off of features that already exist. Now, in other cases, you may even think of using, subtraction between variables, addition between variables, division between variables. It doesn't have to be multiplication, but at least with ml.polynomial expand, it's with multiplication, and it helps simplify a lot of that stuff here to create these new features, to understand interactions between features. So this, importantly, as well as you can imagine with multiplication, it has to be based off of numeric features. So you can't be multiplying Canada by Toronto or Canada by Vancouver. That's not going to work because they're not numeric. So polynomial expand is specifically for numeric features. And you can actually use this value here. So you can see here I've used struct, which is a way to kind of group them together. Struct total hits and total page views, comma 2. 2 is the exponent that you want to be able to multiply things to. So if you were to do comma 3, then you would get total hits, total hits, total hits, total hits, total hits, page views, total hits, total page views, and all the different kind of combinations up to exponent of 3. So hopefully that makes sense. And this is how you can create these extra features for numeric features. But what about for categorical features or text-based features? Now, what you can do with those is you could use ml.feature_cross. So what this does is it simply concatenates your text-based columns to create new features in a way. So it could be that in this particular example, it's not just whether the visitor came from Singapore or Latvia or Sri Lanka, or that they were using mobile phones and desktop phones and mobile phones or tablets. It could be that the interaction, so maybe the mobile phone users in Singapore happen to be much more likely to do something compared to the desktop users of Singapore. Whereas in Latvia, maybe desktop is more important, or mobile or tablet is more important. So by creating this new feature, country device category, using ml.feature_cross, you're taking essentially the interaction between features together as a new indicator, as a new potential signal that hopefully the machine learning model can try to recognize if it's valuable to the end result of predicting added to cart. So ml.feature_cross and ml.polynomial expand are really great ways in which you could augment and create new features based off of numeric data, as well as for categorical or text-based data. So one question you might ask is, well, I've kind of manually entered in total hits. I've typed it out, total hits, comma, total page views, but I want to be able to programmatically fill in the blanks here, so to combine different features together. So how do I automatically find all the numeric features, and how do I automatically find all the categorical features? So to do so, you could use something called information schema columns. So essentially, the end result of this particular query is it takes a look at your table, and for each of the features of the columns in your table, it returns the data type. So full visitor string, full visitor ID is a string, visitor start time is a int, or date is timestamp, and so on. So you could filter this result for string, or for int64, or for float, and then be able to use that as a basis to formulate your queries programmatically. And you can formulate them programmatically using whether you want to use a client library like in Python, which is what I did, or you could even use dynamic SQL, which allows you to programmatically add these into your SQL statement without leaving the SQL language itself. So just some tips there to how do you select the features to bring them into ML polynomial expand and ML feature cross. Okay, so I ran both. Trying to figure out how did each of these perform. So first of all, XGBoost polynomial expand in row number 8 here, right? So everything before was things we talked about. XGBoost polynomial expand here. So I use polynomial expand on all the integer columns, okay? And then that, you can see, decreased my log loss by a little bit, by 0.0004. And ROC also increased a little bit as well. So that means, okay, it kind of picked up on some signal. It's very, very small, but it's some signal there. And then the other thing I did was I added the feature cross for the categorical variables for all the string columns, and I also ran that on top of for the polynomial expand features as well. And you can see that further decreased log loss from to 0.0720, right? And then ROC AUC also increased, just also a minute amount, 0.0003 or so, 36 or so. But in either case, it seems to indicate that polynomial expand and also feature cross help to add a bit more signal to my model. So these are great indications that at least the pre-processing is actually helping my models learn something new. So that is, so far, XGBoost. Now, we can also switch over to a different model, deep neural networks. And this is done very easily, but again, changing the model type to DNN classifier. Okay, so by changing DNN classifier, again, this also means my model name will always start with DNN because that's kind of my way of prefixing all these model names. So how does DNN perform off the bat? So just to let you know, I think deep neural networks, my training time was roughly 3 times slower than for XGBoost. So deep neural networks took quite a bit more time compared to the XGBoost models. And XGBoost models actually took quite a bit longer than my logistic regression models as well. But let's kind of nonetheless see the results that we get. So we have the previous best score from XGBoost at the very first row, where we did extract, date, polynomial expand, and feature cross. And then so for the next one, I tried all the different kind of combinations that we've covered so far, bucketize, n-grams, and so on. And here I'm listing all of them out. Oh, there we go, listing these out. So in row number 10, DNN all, bucketize all here, I've extracted the date and also bucketized them. And that's further reduced our log loss from 0.07. Now it's crossed that extra kind of threshold to 0.06, and the ROC AUC has increased yet again. And then furthermore, DNN all extract date, which is not even doing any sort of bucketizing, that has actually decreased log loss even further. And ROC AUC has actually improved even further, even though I didn't do bucketize in this final row here. So it means that perhaps bucketize was overly generating features that actually was unnecessary, or it was overfitting to the training data, and it wasn't doing so well on the validation data set when I was running ml.evaluate. So that could have been the case. And so it turns out that DNN, with just extracting the date, actually performs extremely well compared to XGBoost with all the features engineered, and also compared to logistic regression. Now, that being said, XGBoost tends to do well with lots and lots of features. DNN, by nature of its modeling, it does more of its own feature engineering because it is a neural network. It does kind of create its own features in a sense. And so maybe for that reason, DNN works really well without necessarily creating all these extra features, well, except for maybe extract date, because maybe that's really, really important. And of course, I also tried n-grams. N-grams did not help for deep neural networks. So that was off the bat. Again, it could have been just that particular data set with n-grams. It just didn't seem to help too much. Okay, so we've covered lots of different approaches for improving this classification task. We covered feature selection, extraction, engineering, and model selection. There's also some other approaches that I didn't go into for the sake of time. Hyperparameter tuning, right? So deep neural networks, you can choose the number of layers, the number of nodes in each layer. For XGBoost, you can choose the number of maximum trees, the tree depth, lots of different regularization techniques as well with XGBoost. So that was not covered at all in this session, but you could try to do that. You can also try to do model ensembling. So by this time, I had created about, behind the scenes, I didn't show all of them. I created about 30 models in total. And I could have done some sort of model ensembling by, assuming that maybe the aggregate kind of result from multiple models could have actually proved to be more predictive than any single model itself. So that's this kind of field of model ensembling that I didn't try to go into, again, for the sake of time. So those are other areas to explore. So overall, in terms of all the modeling that you saw so far in this presentation, I spent about 2-3 full working days just trying to do the best that I could to try to get as close as I could to, getting a really good score, essentially. So how does AutoML perform against my 2-3 days worth of effort? So how does AutoML work? Well, again, super easy. AutoML classifier is essentially the thing you need to change. And again, I changed my prefix. The other thing that you can add here is the budgeted hours. So AutoML, you can budget the number of hours, the maximum hours that you want AutoML to train. So by default, AutoML will train for 1 hour, or maximum 1 hour rather. If it cannot seem to improve any further, it will actually stop before that 1 hour, and that speeds things up quite a bit. You can also set it to 2 hours, 4 hours, 8 hours, and that's essentially what I did. I ran AutoML for 1 hour, 2 hour, 4 hour, 8 hour, and 12 hours to see, first of all, does a 12-hour AutoML model actually perform a lot better than the 1-hour model? And then, of course, does that 1-hour model actually do better than my models? So let's see. Okay, so here are the results for AutoML 1 hour. You can see that based off of my previously best model, which was the DNN model, just by extracting the date, which was a 0.058, AutoML beats it, 0.0577. And the ROC AUC as well has increased from 0.989 to 0.991. And this is just training for 1 hour. So, and then we have the results for the other AutoML models as well. And you'll see it's almost entirely sorted actually by log loss and ROC AUC as is. It's actually sorted here by the number of hours that AutoML has been trained, 1, 2, 4, 8, 12. Okay, and you can see the log loss has, from 0.0577 down 0.574, down 0.056, down 0.55 to 0.0551 for the AutoML 12-hour model. And the ROC AUC, if that's what you're interested in, 0.991, it actually increases a little bit here, increases again, but then decreases for AutoML 8 hours compared to the 4 hours. So there's actually a bit of a flip here. But then AutoML 12-hour is actually the best for log loss and for ROC AUC. So yes, seeing these results after trying to create the best possible model for 2-3 days was, a little bit, it was a little, disheartening. But, let's see. This is just me, right? So what we actually did was we actually ran an internal competition within Google. We had some Googlers, as I was teaching, folks around BigQuery ML, we had them compete, and they only had an hour and a half, so not too much time. And as well, you'll see that across lots of different teams, AutoML came out in front across all these different teams amongst folks who, that being said, they had a limited amount of time to try to create different BigQuery ML models, but still AutoML came on top, which was really, really impressive. You can see here, the first place team had created 8 different kinds of models, and yet still AutoML is just, it's doing really well. Okay, so AutoML 2.4.0. Now it turns out that if you try to use AutoML in data science competitions or machine learning competitions on Kaggle, you may find that AutoML performs really, really well. For, in this case, it was performed strongly for the first 7 weeks of a 12-week Kaggle competition within the top 15%. But as the teams continue to improve over time, AutoML actually did not place as highly. Human teams actually took advantage and beat AutoML throughout this kind of lengthier duration. So what this means is that AutoML is extremely, extremely powerful. At least in my mind, it really beat me quite a lot. It's really good at saving you time if that's what you're looking for, kind of a benchmark of your solution. So if you're trying to compare between AutoML and traditional machine learning models, that you would find with BigQuery ML that is not AutoML, and so you can see here the pros and cons. Use AutoML if you're looking to check if there's some sort of signal in the data. Like, let's say there's a data set that's being placed on your table. Theoretically, it's given to you, and you just kind of want to know if there's some sort of signal in the data. You could try to actually just use AutoML and see if it actually predicts what you're trying to predict to pretty good standard. You can also use AutoML to seek a benchmark. So if you have a data science team and they don't know whether or not they should be investing a lot of time, or they don't know whether or not how much they should improve things to, it could be that AutoML's 0.99 ROC AUC is good enough for your particular business use case. Maybe that's that, and that could potentially save you a lot of money and a lot of time as well. But potentially AutoML may not work as well if you really have some sort of extra domain expertise where you're able to extract some features because you know something about the data that AutoML is simply not able to extract, or if you're able to pair your data set with something else externally that you're not providing to AutoML for some reason, then that's also another way, and you could potentially use AutoML, do something better than AutoML. One con of using AutoML is, of course, it is not easy to audit. So if you're in an industry or you're in a company in which all of your models have to be perfectly explainable, then AutoML is going to be a bit of a black box for you. So use BigQuery ML if you really need to explain your models. But if your model performance is absolutely the highest priority and you have the time and the expertise, both domain and also for machine learning, then I would recommend using BigQuery ML. But that doesn't mean you can't use both at the same time, right? So using AutoML, again, as a bit of a benchmark, and then trying to improve your model from there using BigQuery ML. So as a quick summary, you learn a lot of different pre-processing features to generate new features, extracting dates and times, transform, and how to use that in a create statement, create model statement, quantile bucketize, regex extract all, n-grams, polynomial expand, feature cross. You learned about different different models, logistic regression, XGBoost, DNN, AutoML, and how they kind of compare to each other, both in terms of performance and also in terms of time. And finally, most importantly, is when to use AutoML versus the traditional ML techniques, as you would with BigQuery ML. So that is that. It is a bit lengthy. Hopefully, you enjoyed that kind of journey as I tried to create a model, improve my model, and succumbed to AutoML. I still got to keep working on it, I guess. But that's that. And if you have any questions, feel free to follow me on Twitter or tweet at me. Otherwise, I hope you enjoyed the session. And thank you so much for listening. Cheers.